For the case of MVDR, actually there's a multiplication by 1. The 1 is this value. This value. The 1 here is the F for the broadband case. We don't write here, right? Because it's 1. Don't bother. So you can see the structure of the solutions are basically the same. Okay, so they are the same. Okay, so now to solve for the weight factor, you can compute this with matrix inversion involved. Now imagine if you have 100 by 100 elements, 100 antennas by 100 taps, then what would be the size of the matrix R? It will be huge. 100 times 100, that is what? 10,000. So a matrix of a size of 10,000 by 10,000. Inversion of a matrix of that size is going to be a tough job. When you do your matrix inversion on MATLAB 10 by 10, a split second you get the answer. But if you have a 10,000 by 10,000 matrix inverted on MATLAB, that will take you several minutes or several hours. It's a tough job. So this guy, Frost, he come up with an adaptive algorithm to update the weight iteratively. And that's why this algorithm is known as a Frost algorithm. Do we have to bother? No. I put it there just for your info. Alright, so you don't have to know how this is obtained. To explain this, well, you need another lecture, at least. So this guy wrote a very famous paper back in 1976 to explain his Frost algorithm, and it's a classic actually. Okay, so we have actually explained briefly, the step processing structure. So perhaps one more time, space-time, because array antennas are actually spread out in space. So signals being propagated in space and received by the signal with propagation delay. So the structure here is a spatial structure. Alright, antenna being deployed in physical space. That's why the term space. And when signals are received by the antenna, they will propagate through the FR filter. So you see these are time delay. And the signal being time delayed, they are going to be processed. Being processed, actually if you know signal processing means actually multiplication, addition, and time delay, that's all. So therefore, the processing involves time process, alright? Involve time sampling or involve time samples. That's why across the array, we have space processing. Across the filter, we have time processing. And therefore, the overall structure is known as a space-time processing structure. And these weights are computed adaptively. That's why space-time adaptive processing. Right? And that's the reason why we call this a step processor. Okay, now, why step processing in radar? To explain that, I'm going to go through this very quickly because you've done all this with Dr. Liu last time. So in your Doppler pulse processing, basically that's what you do. In slow time, you send pulse. Right? In fast time, or for each pulse that you send, you sit there and listen for the echo. Right? So when you listen for the echo means what? You have to constantly listen for the return signal. And when you implement this digitally means what? When you send a pulse, you start to look at the signal on the antenna by performing sampling. Okay, so your sampling time corresponds to the so-called range bin. So because you perform sampling